Today we're going to look at factoring examples that use everything we've learned about factoring. When you're looking at a polynomial expression and you want to factor it, which means you want to break it down into a product of simpler terms, the first thing you want to do is make sure that your terms are in standard form, which means the powers of x are going from highest to lowest. I've already written these in that form. After it's in standard form, the next thing you want to do is look for a common factor. In other words, is there a number and or variables that divide into all three of these terms? Well, when I look at 45, 33, and 36, I'm pretty sure that 3 will divide into all three of those. And I notice that all three terms have at least one x in them, so x is also a common factor. So when you're factoring out the greatest common factor, you write the greatest common factor and then you write one set of parentheses big enough for the same number of terms you started with, because you're going to divide each of these three terms by the common factor. So you can think of it as making each one into its own little fraction and simplifying. 45 divided by 3 is 15, and x cubed divided by x is x squared. 33 divided by 3 is 11, the sign stays the same. X squared divided by x gives me x. 36 divided by 3 gives me 12, again the sign stays the same. X divided by x cancels. So you find the GCF and you factor it out. Now you check to make sure you've got every possible common factor out of there. I can't think of any number greater than 1 that will go into all three of these, so we're all set with that. We have to carry the common factor along when we continue to factor this. And when we're looking at a quadratic trinomial, quadratic because the highest power is 2, we want to try to break it down into two binomials, in other words, two expressions that have two terms in them. And we need to find numbers to put in here so that factors of this leading coefficient are going to be on the left side of the two sets of parentheses, and factors of this constant term are going to be on the right side of the two parentheses. So to think of all the possible factors, I draw a line, and on the left side I put the factor pairs for 15, the leading coefficient. So 15 and 1, or 5 and 3, and that's all the factor pairs for 15. On the right side of that line I put the factor pairs for 12. I'm not paying any attention to the sign right now. So that would be 12 and 1, or 6 and 2, or 4 and 3. And that's all the possible factor pairs for 12. Now when I put them in these parentheses, let's say 5 and 3 we're going to go at the beginning. Well, the 5 could multiply by, if you take a pair with another pair, the 5 could be multiplied by either one of these, and same with the 3. So to make sure we don't lose track of whether we've tried both possibilities, on one of the two sides of this little table I'm going to put the factor pairs in the other order. So this one has fewer pairs, so I'm going to write 1 and 15 and 3 and 5. Now I'm going to look for pairs. I'm going to look at one pair at a time on each side, and I'm going to multiply the two top values together and the two bottom values together until I find ones that subtract to give me 11, because the sign of the constant term tells you whether to add or subtract the products, and the middle number, ignoring its sign, tells you what it should end up to be. So 3 times 12 is 36, 5 times 1 is 5, 36 minus 5 is not 11. 3 times 6 is 18, 5 times 2 is 10, 18 minus 10 is not 11. 3 times 4 is 12, 5 times 3 is 15, 15 minus 12 is not 11. So the 3 and 5 didn't work with any of them. Now I'll try the 1 and the 15. 1 times 12 is 12, 15 times 1 is 15, 15 minus 12 is not 11. 1 times 6 is 6, 15 times 2 is 30, 30 minus 6 is 24, not 11. 1 times 4 is 4, 15 times 3 is 45, 45 minus 4 is 41, not 11. So this one didn't work with any of them either. 5 times 12 is 60, 3 times 1 is 3, 60 minus 3 is not 11. 5 times 6 is 30, 3 times 2 is 6, 30 minus 6 is not 11. 5 times 4 is 20, 3 times 3 is 9, 20 minus 9 is 11. So the two pairs that I need to use in my parentheses are the 5 and the 3 and the 4 and the 3. So I'm going to put the 5 and the 3 on the left side of the two sets of parentheses with whatever variable was squared here, but not squared because we're going to multiply those together to make it squared. In the pairing that I found, the 5 was multiplied by the 4. So that means the 4 can't be in the same parentheses with the 5 because those wouldn't be multiplied. The 4 would have to go in the other parentheses. And the 3 was multiplied by the 3, so the 3 has to go in the same parentheses with the 5. Now to determine the signs, since this is negative, since the constant is negative, the 3 and the 4 have to have different signs to make that come out negative. But when we add the outer and the inner products, they have to come out positive. So the outer product here is 5x times 4, which is 20x. The inner product, 3 times 3x, is 9x. This is the larger product. Since we put the 5 and the 3 at the beginning of the parentheses, and they're positive since they don't have a sign in front of them, to make that product come out to have the same sign as the middle, I need to put plus in front of the 4, and that means the 3 is going to get a minus. If this had been addition, they would both get the same sign as the middle. So this is how you would factor the original expression. If it had been given to you as an equation, you would have done all the factoring just like we did, except you'd have to have 0 on the other side of the equation. And then you set each factor equal to 0. And then you solve each of those linear equations, because they only have a power of 1 in them, for x. So here you would divide by 3 to get x equals 0. Here you would add 3 to both sides to get 5x equals 3, and then you would divide by 5 to get x equals 3/5. Here you would subtract 4 from both sides to get 3x equals -4, and then you would divide by 3 to get x equals -4/3. So this expression, this original problem, if this had been an equation set equal to 0, would have 3 solutions. X equals 0, x equals 3/5, and x equals -4/3. Now looking at another example, notice that this one only has 2 terms. We're still going to make sure it's in standard form first, and I'm going to go ahead and put the equals 0 here so we can think of it as an equation. So once you have 0 on one side and it's in standard form, you look for a common factor. I know that 4 goes into both of these, and they don't have a variable in common, so I'm just going to write the 4, and I'm going to divide each of these by 4 to see what I get. 100 divided by 4 is 25x squared, minus 4 goes into 32 8 times with no remainder, and 4 goes into 4 once. Now, on the previous problem, I forgot to mention that before you start doing this table, you should check to see if the two ends are positive perfect squares. They weren't in this case, so I just mentally skipped over that step. But we do have a couple of special forms that we learned about that have shortcuts. These two numbers and this variable are perfect squares, which means they're equivalent to something times itself. And when there's only two terms and those perfect squares are subtracted, there is a pattern for how they factor. If you have a squared minus b squared, that always factors into a plus b times a minus b, the square roots of the two terms in both parentheses, but a plus between one pair and a minus between the other. So the square root of 25x squared is 5x, so I put that at the beginning of both sets of parentheses. And the square root of 81 is 9, so I put that at the end of both sets of parentheses. And then I put plus in one parentheses and minus in the other. It doesn't matter which, because they're the same. So there's no common factor within either parentheses. This is fully factored. So if we wanted to solve the equation, we would set each of its factors equal to 0. Now 4 is never equal to 0, so that part doesn't give us any solutions. But for these other two, we would subtract 9 in this one, and that gives us 5x equals negative 9, and then we would divide by 5 to get x equals negative 9/5. Here we would add 9, and that would give us 5x equals 9, and then we divide by 5 to get x equals positive 9/5. So the solutions for this would be x equals negative 9/5 or x equals positive 9/5. Okay, last example. Here's a trinomial expression. It is quadratic. Its highest power is x. It does go from standard form, highest to lowest powers. I am again going to put the equal 0 here. If you're just asked to factor, you don't have to do the part at the end where you're solving. You just have to stop here if it's just set as a factor. So now I look for a common factor. Well, let's see. The common factor can't be even because this one doesn't end in an even number. Let me see. 3. Remember that a number is a multiple of 3 if its digits add up to a multiple of 3. 4 plus 8 is 12, that's a multiple of 3. 1 plus 6 is 7 plus 8 is 15, that's a multiple of 3. 1 plus 4 is 5 plus 7 is 12, that's a multiple of 3. So I do have a common factor of 3. So there's no variables in common, so I'm just going to divide each term by 3 to factor out the 3. 3 goes into 48 16 times with the x squared. 3 goes into 16 5 times with a remainder of 1, and 3 goes into 18 6 times, and the x is still there. 3 goes into 14 4 times, that's 12, so the remainder is 2, and 3 goes into 27 9 times. Now, my 3 is factored out. There's no other number that will divide into all 3 of these because 7 and 1 and 49 are the only numbers that go into this, and 7 doesn't go into either one of these, and neither does 49. Dividing by 1 doesn't do anything for us. So now I look at the ends. They're positive perfect squares. Now I could do this using the table method, but because it looks like it might be one of those special patterns, I'm going to try it that way. So this one doesn't have two terms with subtraction, so it can't be a difference of 2 squares, but it might be a perfect trinomial square. If you have something that looks like a squared plus 2ab plus b squared, that always factors into a plus b, the quantity, squared. And if this was minus, this would be minus. So since these are both perfect squares and positive on the end, I got to carry that 3 along. I'm going to see if it's a perfect square. So first I'm going to put the square roots of the two ends in. The square root of 16x squared is 4x. The square root of 49 is 7. Now, the way you check to see if it actually is this type of problem is you multiply these two things together, so that would be 28x, and then you double it. 28 times 2 is 56x. If this number is equal to this, so this expression rather is equal to this, then it is a perfect trinomial square, and whatever the sign of that middle term is goes in between. Now here once again, if we were solving this, 3 can never equal 0, so that doesn't give us any solutions. And 4x plus 7 can equal 0. You don't have to do it twice because it's the same answer whether you do it once or twice. So we would subtract 7 to get 4x equals negative 7, and then divide by 4 to get x equals negative 7/4 would be the only solution for that quadratic equation.